In this next video, 1.3, we're just going to look at what are some measurable factors for monitoring reaction rates. So in the previous examples, we kind of just looked at reaction or reactants consumed or products produced, but there's other things we can do to monitor how fast a reaction is going. So in fact, there's 7 properties that can be monitored, and it's going to be your job to look at an equation and determine, or reaction, and determine which of these 7 properties could be used to monitor a reaction rate. So the first one is color change. So to monitor color change, there has to be a color. Either it's going to be a colored reactant being consumed or a new color product being formed. And they measure this quantitatively using a spectrophotometer. So they'd be looking at the concentration of whatever color is produced or whatever color is being consumed. If you were calculating this rate, it would be a change in color intensity over time. A good example of this one would be the reaction of copper with nitric acid. Copper is a brownish metal, and nitric acid is colorless. And when these two react, they produce copper nitrate, which is blue. And they also produce nitrogen dioxide, which is brown, and water and heat. So the key thing is there has to be a color change. So since you're consuming brown and producing brown, you couldn't use brown to monitor this, but you could look at the intensity of blue being produced. So I've got a video here that just demonstrates this color change property. All right, so they don't really talk in this video, so I'm just going to scroll through. But what they've got in the test tube here is the colorless nitric acid. And then in this jar right here, they have the copper. So they're going to just pour some copper into their hand. And here you go. You can see that it is copper colored. So we called it brown, but really it's like copper color. Horrible videoing. And then what's going to happen is that they are going to add the copper into the nitric acid. And then this is the reaction that's happening. So you can see that this brown nitrogen dioxide is being released, which is super toxic, and you'd want to make sure that you're really careful with around it. But you can see in the test tube here, right? This was a colorless acid, and we put in a brown copper colored copper, right? And so there's this change in color. So right now you can see that it's kind of green. As the reaction continues, right, you can see this brown gas is being formed. And then at the end here, they go back and they show a really nice thing, and you can kind of see it be a bit more blue. So what they could do is use a spectrophotometer to measure this color change in color intensity over time. So the more the product is produced, the more blue there would be. So the more of that copper nitrate that is produced. Awesome. So you can use color change, obviously, when there's a color change. So this one's going to be fairly obvious in a question because they will tell you colors. The next one is temperature change. So temperature can either be, or not temperature, heat, can either be consumed or produced in a reaction. So hopefully you know the words exothermic versus endothermic. So when a reaction is exothermic, it's releasing heat, and when it's endothermic, it's consuming heat. And so what we could look at is the change in the temperature of the surroundings over time. We would do this in an isolated container, something like a calorimeter if you've taken physics. But what we'd be looking at is if it was an exothermic reaction, you'd have your reactants, A plus B, producing your products, C plus D, and heat. So if a reaction is exothermic, it's producing heat, and the temperature of the surroundings will increase over time. And that's something that you could monitor. If it was an endothermic reaction, you'd have your reactants, you'd have your products, but this time heat would be consumed. It would be one of your reactants. And so if heat is being consumed, the temperature of the surroundings will decrease. Awesome. The next thing we could use to monitor a change or a rate of reaction would be pressure or volume changes. These two are very much tied. What will happen is you can monitor pressure if the volume is fixed, or you can measure volume if it's not fixed. So when a chemical reaction is consuming or producing a gas, and this is the key word in this sentence. So when can you use color? Well, when they state there's a color change. When can you use temperature? When they state that heat is consumed or produced. When can you monitor a reaction rate using pressure or volume? When the reaction is consuming or producing a gas. Now, volume changes can be measured using water displacement or a balloon. Pressure changes can be measured using a manometer or a gas pressure sensor or a balloon. So, what I'm going to do is show you just a couple videos on monitoring volume and pressure changes, and then we'll talk about how you would look in a reaction to determine if you could use this as a method of monitoring. All right, so I'm going to let this one play because I actually think this is a really good one to watch experimentally. Like, this is how someone would measure and capture a gas produced and then measure its volume. So I'm going to hit play and hopefully this is all going to work.
This is a tutorial video showing you one method that you can use to collect data that will allow you to calculate the rate of a chemical reaction. In this video, we're going to look at how to measure the rate of a reaction that experiences a volume change because it produces a gas. The rate of a chemical reaction is its speed, or how quickly it's going. In order to calculate rate, we need two pieces of information. Firstly, we need to know how much reactant is being used up or product is being made. And this could be expressed as a mass in grams, a volume in centimetres cubed, or an amount in moles. And then secondly, we need to know how long this process takes, usually in seconds. Once we have those two pieces of information, we can complete a calculation to work out what the rate of a reaction is. We're now going to look at how you can actually get that data. You'll meet many reactions within GCSE chemistry that produce a gas, and we can measure the rate of these reactions by collecting the gas, seeing what the volume is, and measuring this over time to calculate the rate. There are two key ways that you can do this. In the first method, you use a piece of equipment called a gas syringe. Gas syringes allow you to collect and measure the gas directly, so they're very accurate, but also they're often fragile and quite expensive, so lots of schools don't have easy access to them. What you're more likely to have done instead is collect gas over water. This involves using an upturned measuring cylinder full of water and a delivery tube that comes from the conical flask where your reaction is happening into that measuring cylinder. As the gas is produced, it will displace the water and push it out. So by reading the size of the gas bubble on the measuring cylinder, we can determine how much gas has been produced. In this video, we're going to look at the reaction of magnesium strips with hydrochloric acid, which produces bubbles of hydrogen gas. I start by measuring 20 centimetres cubed of acid using my measuring cylinder. This needs to be the same every time I complete the investigation, as the volume of acid should be a control variable. I pour this into my conical flask, and the narrow neck of the conical flask means I can attach a bung and a delivery tube to collect the gas. I'm going to put this piece of magnesium into the acid, but first I need to sort out my delivery tube. This is going to go up and inside the measuring cylinder full of water, so as the gas is produced, I'll be able to collect it, it will displace the water, and I'll be able to read off the volume. Starting from 0. Now this next bit is a little bit tricky with just one pair of hands, but I start the stop clock, add the metal into the acid, and then attach the bung. And then every 15 seconds, I'm going to look at my measuring cylinder and write down what the volume of gas collected is. We're now going to fast forward. Eventually I can see that all of the magnesium has reacted and no more reaction will take place, so I stop the reaction. There are two things to bear in mind when you draw the results table for this reaction. One is that your units should only be in the header of the table. You should never have any units in the body with your actual data. The other thing is it's important to include the volume at time 0, as people often forget and miss this row out. Now that I've collected my data, I can plot these onto a graph to make it easier for me to identify trends. It's still important to identify what the units are, and these are listed in the axes labels on the graph. You may be asked to draw a line of best fit, and this should follow the overall pattern of your data. Here my data are forming a smooth curve, so my line of best fit should also be a smooth curve. You can see here that my first reading was actually quite low, and this is quite common for this experiment because chances are some gas was lost while I was trying to put on my bung, so that first reading may not have been accurate. I don't want to force my line of best fit to go through that piece of data, I just draw a curve that follows the general shape of the data. You could be asked to calculate a mean or overall rate of reaction for this reaction. In doing so, it's important to identify where the reaction actually stopped. Although I took another reading after 105 seconds, actually no more gas had been produced in this time because all of the magnesium had been used up. So in calculating the rate, I want to go from where the graph becomes flat and plateaus. So to work out
Okay, I'm going to stop the video there. I was like, oh, I should let it keep playing because this is actually like a good demonstration of our lab. But what I'll say is this could be a good video to go back to when you're collecting lab data. But I'm going to stop it there. And then this next one is just using a gas pressure sensor. So I'm actually going to turn the volume off. I'm just going to hit play on this one and just fast forward so that you can see. So what's happening here is that they are just adding calcium carbonate to hydrochloric acid. Same idea, they put the bung on, and then the difference is that instead of using the volume of gas to displace water, they're actually just putting the bung on, and then they've got this fancy pressure sensor where they can actually literally just get readouts for the change in pressure over time, which is really cool. And again, you would take these pressure samples at different time intervals, right? And then you could produce this graph. And same thing, their rate of reaction should be quicker, and then it'll slow down, which is part of the next part of the thing that we're going to talk about. Awesome. Okay. So that is measuring pressure and volume changes. So again, it kind of depends upon your measuring instruments, which one you're going to use. And, sometimes it's simply done with a balloon, right? They'll put a balloon over top of the flask. And then as the gas is produced, you would see the balloon inflate, 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 inflate. But what we're going to be looking at is how do you know when you can use pressure or volume change as a method to monitor reaction rate? So, what you're going to be looking for is a release or a consumption of gas. So, what you're going to do is look at the left and the right hand side of your equation and determine how many moles of gas are on each side. So, for example, for this reaction of zinc and hydrochloric acid, there are no moles on this reactant side. Whereas on the product side, you can see that you have this gas produced. So you have one, because there is a one out front of here as your coefficient, there's 1 mole of gas produced. So if you think about this reaction over time, every time this reaction occurs, you're going to be producing more or 1 mole of gas. And so if this reaction can happen multiple times, if you have enough zinc and enough hydrochloric acid that this reaction can happen over a period of time, you're going to get more and more gas produced. If more moles of gas are in the products, the pressure or the volume will increase over time. Whereas looking at the second one, on the left-hand side, we have 1, 2, 3 moles of gas on the reactant side. And on the product side, we have 2 moles of gas. So for this one, there's more moles of gas in your reactants. So your pressure or volume would do what? Well, you're producing less gas than you started with. So your volume or pressure will decrease over time. But both of these reactions, you could use pressure or volume to monitor the rate of reaction. Whereas if you had something that didn't have any gas, or maybe had equal moles of gas on each side. So, for example, this one you have 1 and 1, so you have 2 moles of gas on the left, and you have 1 and 1, you have 2 moles of gas on the right. So, if equal moles of gas, the pressure or volume will not change over time. So, you wouldn't be able to use pressure or volume to monitor the rate of this reaction. Awesome. Okay. Next one is mass. So this one's really important that you either generally have a solid reacting. So one of the ways of monitoring a rate of reaction over time is that if you have magnesium, for example, reacting with hydrochloric acid, producing hydrogen gas and magnesium chloride as an aqueous solution, that solid chunk of magnesium, its mass would do what over time? Right? If it's being consumed in the reaction, the mass of the solid would decrease over time. So potentially you take that solid out of reaction and measure its mass over time. Now that would be quite difficult to do. And so instead, what often happens is that if you have an open system with gas produced, you can just look at the mass of a system. So instead of having to take out an individual reactant like the magnesium solid, you could have something like a calcium carbonate breaking down to calcium oxide and calcium or carbon dioxide. And so you've got this gas being produced. If you have an open system where the gas is allowed to escape, then what would happen to the mass of your system over time? Well, as the carbon dioxide escapes, you're losing contents, which means the mass of the container and its contents will decrease over time, right? So the key thing with this one is that you're going to be looking for a gas evolving or potentially a solid as one of your reactants that's not there in the product so that you can monitor the mass over time. The sixth one is concentration change. So when there's a change in concentration of a specific ion, then you could monitor its change in concentration over time, again, often with a spectrophotometer. So if you had a reaction like magnesium solid plus HBr going to hydrogen gas and magnesium bromide, then what would be happening on the ionic level is that you'd have this magnesium solid. And then whenever you have an aqueous solution, that actually means it's just ions in solution. So you have two hydrogen ions and two bromine ions, right? And then the product side, you have this gas evolving. So the gas is going to stay a gas, but then you have magnesium ions and bromide ions, right? So this magnesium bromide would be broken up into magnesium and bromine ions. So what's going to happen over time? Well, there's ion changes. Magnesium starts out as a solid and then it's being produced as an ion, which means the concentration of magnesium would increase over time. What ion would decrease? Well, is there something that is present on the left as an ion and not on the right? Well, look at hydrogen. Hydrogen gas is evolving, but it's starting as a hydrogen ion on the left-hand side. So the concentration of hydrogen ions would decrease over time. So if we had a way of monitoring the concentration, either using like a spectrophotometer type idea, or maybe titrating your solution, or maybe number 7, but we could monitor the concentration of magnesium over time. The magnesium ion should increase and the hydrogen ion should decrease. Now there's one other ion here. You've got bromine on the left and you've got bromine on the right. Since it's present as a reactant and as a product, then that concentration is not going to change and you could not use it to monitor the rate of reaction. Okay, last thing here is changes in acidity. Changes in acidity is really just the same as number 6, but we're talking specifically about your hydrogen ion. So if you had a reaction like magnesium solid plus hydrochloric acid goes to magnesium chloride and hydrogen gas, if you look at this, the aqueous solution contains hydrogen ions, whereas in your product side, it's tied up as hydrogen gas. So what's going to happen? Well, as the reaction proceeds, the hydrogen ion concentration would decrease. And if you think back to acids and bases, a decrease in hydrogen ion concentration would cause an increase in pH, becoming less acidic. So what we could do is measure the pH of this reaction over time. So again, we're really kind of measuring the hydrogen ion concentration, but in terms of pH. Okay, so those are your 7 methods that you can use to monitor reaction rate. And what we're going to now do is look at 2 examples and determine for each example what methods could be used to measure the rate of reaction. So the first one here is calcium carbonate and hydrochloric acid producing calcium chloride, carbon dioxide, and water. Could we use color? Well, they haven't stated a color change, so we can't use color. No color stated. What about temperature? Well, again, if you look at this, to use temperature, you have to have a heat term. So we can't use temperature because there is no heat term. We don't know whether this reaction is endothermic or exothermic. Okay, what about pressure? Now, when we talk about pressure, we're really talking about pressure and volume. So what about pressure and volume? To use pressure and volume, there has to be a gas consumed or a gas produced. If you look here, you have a carbon dioxide gas produced. So both of these could be used to monitor the reaction rate. So we could monitor the rate as the change in pressure or volume over time because gas is produced. Now, what would happen? You should have an increase in pressure or volume over time. Okay, so thinking about that video that you watched, you would just take it over specific times and measure the volume of water displacement or of pressure change. Okay, next one, mass. Well, we started with a solid and we produced a gas. So could we use mass? We sure could. So this is numbers 3 and 4. Number 5, we can use mass. So what I would say is that we would calculate the rate in the change of um, entire system over time. Because the gas is evolving or being produced, whatever you want to use, there should be a decrease in mass over time. Okay. Lastly, what about ion concentration and specifically pH? So if we look at this, we could do multiple things. So for number 6, if we look at this one, we've got calcium tied up in a solid, and then we have a calcium ion produced. So you could look at the rate as the change in calcium ion over time. Anything else? Well, hydrochloric acid, so the hydrogen, we could do hydrogen specifically, but let's talk about that in number 7. The carbonate kind of gets broken up, so we're not going to do that one. And then the chloride stays an ion on both sides. So we could do the concentration of a change in ion if we wanted to do calcium, or more specifically, we could do rate as the change in hydrogen ion concentration over time, because there will be one. So if you look at here, you've got hydrogen ions in the hydrochloric acid, and then over here you've got your hydrogen tied up in the water. And so what's going to happen is you're going to have a decrease in the hydrogen ion concentration over time, which is going to lead to an increase in pH over time. So for this reaction, you could use pressure or volume change over time, you could use mass of system over time, and you could use ion concentration and specifically hydrogen ion concentration to look at the change in pH over time. All right, so pause the video, see if you can give this one a go. This one, it just says 2 methods. So if this was a test question, there's probably more than 2 methods that could be used. But can you determine 2 methods that could be used to determine experimentally the rate of this reaction? To give you a hint, there's the 7 options up top. And so you're going to pick 2 of them down here. All right. So I'm just going to cheat. Could we use color? Well, it says a solution of copper 2+ are blue, whereas a solution of silver are colorless. Could we? Well, we could potentially use color, right? Because we've got this copper that is going to be produced, so this copper ion that's going to be produced, and it's blue, whereas the silver ion solution is going to be colorless, and then this is probably going to be that brown color. You could use color change over time. So I would say something like an increase in blue over time. Okay. Secondly, what else could we use? So if the second one is temperature, could we use temperature for this one? Yes. Why? Because heat is released, making this an exothermic reaction. Thermic, which means you would have an increase in temperature over time. Okay. What about 3 and 4? 3 and 4 being our pressure and volume. Is there a gas evolved? Nope. Okay. What about mass? Well, we have a solid as a reactant, and we also have a solid as a product. And again, no gas evolved. So like if you knew you could specifically take out copper solid and monitor it, but that would be quite tricky. And since no gas is evolved, you can't do mass of system over time. So I'm going to skip that one. So let's go for ion concentration. So the third one would be ion concentration. And you'd have 2 choices here. You could do an increase in the copper ion over time, or you could do a decrease in the silver concentration over time. And then if we're looking at the seventh one being pH, pH you specifically have to have a change in hydrogen ion concentration. And in this one we have a change in copper and a change in silver, so we can't use pH as a method. So again, there's three options. You would be picking two of those three, and you wouldn't have to describe all three. All right, go and practice some questions.